Okay, I'm happy to introduce, we saved the best for last. Medha is a PhD student at UW. It's one of our IFML partners, so happy you could make it down here and close us out with the last talk.
Thank you. Thank you for inviting me here. This has been a workshop of amazing talks. Hope I can close it all nice and good for you all. I'm going to talk about.
Are you okay there? Is the laptop?
I will just have to walk to switch, but that's fine.
Okay.
Okay, so I'm going to talk about this work titled Heat Flow Through Doubly Stochastic Self-Attention. This is a joint work done with Garrett Mulcahy, who is also a PhD student at UW in math, and then two professors, Soumik Pal and Zaid Harchaoui, also at UW. All right, so briefly, I'm going to consider these special kind of self-attention matrices called doubly stochastic self-attention matrices, and then show how a particular configuration of these in the mean field limit converges to a heat equation. And that's just an interesting observation, which also opens path for other kinds of questions, like what are other kinds of mean field limits we get from other configurations of self-attention matrices. So we'll look, let's dive deep. So the outline of the talk is going to be like this. First, I'm going to briefly introduce self-attention mechanism, then go into what do I mean by doubly stochastic self-attention mechanism, then explain what is the infinite particle and time discretized picture of these doubly stochastic self-attention mechanism. And then I'm going to establish a relationship between this doubly stochastic self-attention update and the barycentric projection, which has connections to optimal transport. And I'll define these quantities that are highlighted over here. And then we are going to go over three main results from a paper and then look at quick simulations. So the first thing on agenda, what is the transformer self-attention mechanism? I think you've already seen this in the talk before mine, or the one before that. But I will write it down in its residual form. So suppose we have an initial set of particles, x1 through xn, that are sampled from some initial distribution, rho 0. When they go through a self-attention layer, they undergo this kind of update, where xk plus 1 is xk plus this sum, so sum from j1 to n, and then I have these weights kij1, and then I multiply them by the value of the jth particle obtained by this linear operation via this WV matrix. And then xik is going to denote the position of ith particle after it has gone through the kth self-attention update.
Can I ask a question?
Yes.
I thought that the dependence on x would be, cubic.
Sorry?
So in this attention layer, why would the dependence on x be just linear?
Here?
Yeah.
It's not linear because when we unpack what this k is, it actually has x's in it, and that's my next slide. So basically, when we unwrap this, yes, so WV is the value matrix, and then Kij is Kij1 applies softmax on this cost matrix, whose ijth entry is given by the dot product between ith query and jth key, where the query is obtained by multiplication via this matrix WQ, and then the key is obtained via multiplication by this matrix WK. And then this is the whole self-attention update. There has been a lot of previous work on trying to understand self-attention mechanism as function of nonlinear functions acting on probability distributions. One of the first works that introduced this thing is the first citation over here. They formulated self-attention mechanism as a nonlinear transformation on probability measures. So you understand self-attention as push forwards happening on probability measures, and then you try to understand how is the probability distribution of particles or tokens changing as it undergoes the mechanism. And then there are other papers that try to study, for example, its Lipschitz smoothness, its Lipschitz continuity. We are specifically interested in this last citation over here that proposed something called syncformer instead, where they introduced doubly stochastic self-attention via Sinkhorn algorithm, and hence the name syncformer. So let's look at what this syncformer is. Recall, this is the transformer self-attention mechanism that we just saw. In the syncformer self-attention mechanism, we replace that K1 by K infinity. And the only change that is happening is that instead of applying softmax to C, we instead apply Sinkhorn to C. What is Sinkhorn is this algorithm over here, where we take the cost matrix C, but instead of only row normalizing it after taking the exponents, but instead of only row normalizing it, we alternatively do row and column normalization until a doubly stochastic version is obtained, in that the row sum and the column sum both is equal to 1. So in the end, this matrix K infinity is going to be doubly stochastic.
Is there a version of this for causal attention?
Sorry?
Causal attention?
Causal attention. Sorry, I'm not familiar with
Oh,
that.
no.
Okay. So yes, so this is our doubly stochastic self-attention update, which does some kind of transformation to the particles. But then what happens in the infinite particle limit? It is going to do some kind of transformation on the densities, and that is what we are interested in. So if we look from the density perspective, we are applying these push-forward maps to the densities, where the push-forward function is given by this guy over here. So rho k plus 1 is this push-forward map, T rho k, applied on the previous density, rho k. And then this is the push-forward function. Recall, in the finite particle setup, we had this update over here. So in the infinite particle limit, this sum becomes an integral. And then the matrix capital K is replaced by this kernel K infinity. And then the kernel K is also obtained similarly via the Sinkhorn algorithm. And each sum just becomes an integration over here. And for the particles, there is always this interplay between the density and the particle picture. So for the densities, we write it as an update via push forwards, and for the particles, we write it via this update over here. So now we have looked at the infinite particle picture, or update looking at doubly stochastic self-attention as updates on density. Now let us look at the time discretized picture. So recall, this is the doubly stochastic self-attention update for the particles. Now this is something that people do all the time in neural ODEs, where they look at layers as the time variable. And if we do that, the above update can be seen as the time discretization of this ODE over here, where if we take the forward Euler time gap 1 discretization of this ODE, we get the above update. So if we look at this ODE, and think that this is the ODE which is driving our self-attention mechanism, then on the time axis for time k plus 1 epsilon, if we choose epsilon to be the gap between consecutive layers, to be the time gap between consecutive layers instead of 1, the position of a particle at time k plus 1 epsilon can be given by this update equation over here, where I replace all the xk's by the position of x at time k epsilon now instead of time k, because I have reparametrized the gap between consecutive layers by epsilon. So, all right, so this is the, so the above update, this update over here gives me the time discretized particle update of the doubly stochastic self-attention mechanism. Now this update for the x of k epsilon, these particles will explode to infinity as k keeps increasing. So in that, all the tokens will eventually explode away to infinity. So this paper, the Singh-Farmer paper, Sanders et al., that came out in 2022, they reparameterized the xk epsilons by this position by these tokens z of t, which is given by z of t is equal to e raised power minus t v xt, and they further introduced the bandwidth parameter epsilon, which scales this matrix wq transpose wk and the wv matrix by epsilon. And ultimately, I'm hiding away some mathematical details over here, but the update equation, similar to the update of xk plus 1 epsilon for the z's, for the reparameterized z's, is given by this guy over here. I'll stop for any questions because I'm hiding away some details. Yes?
So how do you compute the synchrone? Like, for example, in discrete time you did odd times, you did row normalization, even times you did column normalization.
Yes.
When it becomes continuous, how do you compute the
Oh,
synchrone time?
it is over here. So, so it's the same. It's the same mechanism. So for even times, I do the normalization along the second argument, and then for odd times, I do normalization along the first component.
But then now this L plus 1 becomes L plus epsilon, right? In your final solution.
Oh, okay. So this is different from the updates that are happening for the self-attention mechanism. We run this process the guarantees would say run this infinite number of times, but if you run it, say, 1,000 times, then you should be able to get a doubly stochastic kernel. And then you plug that in.
It's unfortunate that you use the same k. You use k for x to the k.
Yeah.
And then the k infinity.
Oh, I see. Yes. Yes. So yeah, this k is the kernel, and that k is the updates. Yeah.
I have a question. So,
Oh yes.
so just like my understanding, so the synchrone is generalized softmax. And what's the relationship between synchrone and softmax?
Softmax, if you think of it like this, if you ran synchrone for just one update, then that would give you softmax. So if you did just row normalization once, that would give you softmax. But then if you kept going on with the alternate normalizations, then you would get synchrone. Yeah. Yes. So this is the update equation that we really want to focus on. This is the normalized and time discretized and infinite particle update that we want to focus on and understand what happens in the mean field limit of this update. So there are these 4 configurations of query, key, and value matrices, Q, K, V, that we want to focus on over here. And we empirically try to understand what happens in the limit for these 4 different configurations. And this is what the limiting geometry is. If I have a bunch of particles and I look at the first configuration, Q transpose K is positive definite, and then V is identity matrix. And if I keep running the self-attention mechanism over and over again, the particles tend to converge to vertices of a polytope. And I'll show pictures for these things. If we are in the second setting, in that the Q transpose K is positive definite and the largest eigenvalue of V is positive, then they converge to a hyperplane. Then here they converge to polytope and subspace. I'll show what the picture looks like. And then for the last one, what seems to happen is that the tokens just diverge to infinity, even though we did the scaling to prevent that from happening when it was happening obviously. because I promised pictures, so this is the first case. We have a bunch of particles, and then we keep running this, and after 5 seconds, we see that this kind of convergence starts happening on the vertices of a polytope.
Is the polytope contained in a hyperplane?
Not necessarily. I can go back.
It looks like your second case includes the first case.
It's not necessarily in a hyperplane.
Okay.
Yeah, this is not necessarily a hyperplane. If I run it for different configurations, it will, the vertices will change, but you'll notice that they're not on a hyperplane.
But the first case you're assuming V is the identity, and the second case you're assuming that the top eigenvalue of V is positive. So
Yes. So it can have
the second case includes the first case.
In the second case, some of the eigenvalues can be negative as well. It's only that the largest eigenvalue is greater than 0.
Okay.
Sorry, does V here, can you remind me what V?
It's the value matrix.
Is that just the weights, or is that the weights in the transformer? Is that?
Yes, so the transformer, recall, is composed of 3 different kinds of these weights or these matrices: the query, key, and value. So V is the value matrix, and then Q and K are a query and key matrices respectively. Query and key matrices appear in the self-attention matrix, and then value matrix is the one whose weighted average we take to get the next update of the self-attention mechanism.
And you're assuming that V here is a square matrix?
Not necessarily. So if the particles are, say, in dimension D, the V matrix can be some P cross D. So it can map from D dimension to some P dimensional space. Yeah, not necessarily. And then this is the second case where we see after 5 seconds, 5 time units, the particles are starting to converge on a hyperplane. If we look at the third one, the particles are converging to on some subspaces that are located on the vertices of a polytope. And then in the third one, they completely diverge to infinity, and you can see that by the increasing x, y, and z axis. So we are interested in this last one. We're interested in all of them, but for this paper, we're interested in the last one. And what we show is that as epsilon goes to 0, so recall epsilon is what we are using, is the bandwidth parameter or temperature parameter that we are using to parameterize the gap or the width between consecutive self-attention layers. What we prove is that if epsilon goes to 0, the densities converge to the heat equation. Concretely, first as a graphic, if these are my densities at time 0, 1, 2, 3, at time 0, epsilon, 2 epsilon, 3 epsilon, we show that as epsilon goes to 0, these densities would converge to how the densities would evolve in heat equation. Concretely or mathematically, we know that for the doubly stochastic self-attention, the update is given by this rho epsilon k plus 1, which denotes the density at k plus 1th iterate is given by this push forward, where the push forward map is given by this guy over here. Under the fourth configuration that we were interested in, WQ transpose WV is identity, and then the WV is negative identity. Under this transformation, under this configuration, the self-attention update is given by this. And we are interested in what happens when epsilon goes to 0.
Excuse me, do you have an epsilon in front of the integral or not?
Sorry, where?
So is it x plus epsilon times the integral, or just x plus, or what you wrote there is correct?
This is correct, but yeah, that's a very a nice observation. So yes, there is an epsilon earlier, but because I did the epsilon scaling earlier to obtain, because I did the epsilon scaling earlier on the WV matrix and WQ transpose WK matrix, there was an epsilon in the denominator, and then they got cancelled. Okay, so just to put it out there in the center, this is this is the self-attention update. 2 times identity minus this integral, and then using this function to push forward as the push forward. We can write this down, this integral, as b rho epsilon, which we will call barycentric projection, and I'll define this quantity later and draw its connection to optimal transport. But we are interested in this object now, 2 times identity minus b. And what happens when epsilon goes to 0? Or if I define this piecewise constant curve where rho epsilon t is given by rho epsilon k if t belongs, if t is between k epsilon and k plus 1 epsilon. So if I define this piecewise a constant curve, I want to ask the question that is there a curve rho t such that rho epsilon t converges uniformly to this curve as epsilon goes to 0. And our claim is that the claim made by Sanders et al. Is they hypothesize that it should converge to a gradient flow. That gradient flow is heat flow, whose equation is given by this quantity over here. So this is the PDE for heat flow. And then we have already defined our self-attention flow, which is the one above that, written in this piecewise constant manner. And what we show is that uniformly, between time 0 and some capital T, so we choose this capital T, and for this fixed interval 0 to t, uniformly these curves do converge to each other as epsilon goes to 0. So now I am interested in understanding this object B that we showed earlier, and which defines the self-attention. So just a couple of quick notations from optimal transport before we go into what that B actually is. So if mu and nu are 2 probability measures, we say that a gamma defined as a probability measure on the product space, RD cross RD, is a coupling or a transport plan between mu and nu. And the set of all of those is denoted by this capital pi mu comma nu. If for all measurable A and B, to all measurable sets A and B in RD, gamma of A cross RD is mu of A, and then similarly gamma of RD cross B is nu of B. So so basically gamma is forming a coupling between the measures mu and nu. And then the second is the transport map. So we say that a measurable function T is a push forward from mu to nu, denoted by this quantity over here, T sharp mu is equal to nu. If for all measurable sets A in RD, nu of A is equal to the mu of T inverse of A. So these are just a couple of notations for optimal transport, but then we are interested specifically in the entropy regularized optimal transport problem. What this problem is this optimization problem over here. So entropy regularized optimal transport problem is, it basically minimizes the, for the squared loss, it minimizes the cost, the squared cost, plus this regularization term, where the regularization is in form of this guy, which we know as scale divergence. And then the optimization is done for all couplings between mu and nu. So it's basically giving me, like the name suggests, an entropy regularized version of the optimal transport problem. And what we are interested in is the solution of this optimal transport problem, of this entropy regularized optimal transport problem. Let's denote it by pi epsilon, and that is called the Schrödinger bridge between mu and nu. And where this comes in, where this is helpful, is that recall that barycentric projection we were talking about earlier, the object B that appeared in the self-attention update. there is a close relationship over here. So here we define the barycentric projection from mu to nu as this conditional expectation with respect to pi epsilon. So pi epsilon, the Schrödinger bridge that solves the entropy regularized optimal transport problem between mu to nu, if I take the conditional expectation of y given x, where x comma y is distributed as pi epsilon, that is the barycentric projection. And now I am only concerned with the case where mu is equal to nu. So I consider same marginal. And now I look at this object pi epsilon, which is in the non-entropy regularized version. If I was just transporting some measure mu to mu, what would be the optimal coupling? It would be identity. It would be just a diagonal. If we were in the discrete case, it would just be a diagonal matrix. So here, but because we are considering an entropy regularized version, it would be a fuzzy version of the diagonal matrix, or a fuzzy version of the identity map. And now if I consider, and for this same marginal, if I consider the Schrödinger bridge with same marginals, and then look at its conditional expectation or its barycentric projection, that is the object that is coming up in my self-attention update over here. So what we are really seeing is that the self-attention update can be written as identity minus epsilon times this quantity over here. And this velocity field over here, the barycentric projection of Schrödinger bridge with equal marginals rho minus identity by epsilon, this should be very close to the velocity field that we have in the heat equation. Any questions at this point? Okay, so now three main results to make this concrete. So the first result we prove is that, and which will help us prove the uniform convergence, which is our main goal, is that this Schrödinger bridge with equal marginal is very close to the law of Langevin diffusion, law of stationary Langevin diffusion between time 0 and epsilon. So if I consider some rho of the form e raised to the power minus g, which is the strong solution of this stationary Langevin STE, and I consider L rho epsilon as the law of x at time 0 and epsilon, then pi rho epsilon, the Schrödinger bridge with equal marginal rho, is very close to the law of this Langevin diffusion between time 0 and epsilon. So what we show is that these objects are very close. If I run Langevin diffusion, a stationary Langevin diffusion at time 0, and then stop it at time epsilon, and I look at this joint law, it's going to be very close to the solution of the entropy regularized optimal transport problem. And how this is useful. So if we look at the heat flow, the object that we are going to show we converge to, if we look at heat flow, that is the PDE we call. In the particle picture, it's given by this guy over here. So at any time t, rho t, is given by the push forward xt of rho 0, the starting measure. And then xt is the, in the particle picture, it is governed by an ODE, whose velocity field is given by -1/2 of the score function. A gradient of, of the -1/2 of the score function. So this is the heat flow. But now if we, using result 1, which showed that this equal marginal Schrödinger bridge is very close to the law of Langevin diffusion, stationary Langevin diffusion between time 0 and epsilon, intuitively, this is not mathematical, this is just a rough sketch, but the barycentric projection, which is the conditional expectation with respect to the Schrödinger bridge, should also be approximately equal to the conditional expectation when taken with respect to the law of Langevin diffusion, the L rho epsilon. which is going to be equal to x minus epsilon over 2 gradient of g. Recall g is coming up from this SD we defined for the considered Langevin diffusion, which is this guy over here, x plus epsilon over 2, which means that the velocity field we were looking at in our self-attention update is going to be approximately equal to the score function divided by 2. And so yes, so the velocity field that we were observing in our self-attention update is going to be approximately equal to the score function divided by 2. Now here are two main things that we get from here. We see that it matches the Euler approximation of the heat equation. In the heat equation, our velocity field was this guy. And the velocity field, the negative of the velocity field we are observing by considering this rough approximation of the Schrödinger bridge by Langevin diffusion is this guy over here. And these two objects are the same. I mean, we're using the negative of this velocity field, but these objects are the same. So they should approximately be the same. And then the second is that this barycentric projection of equal marginal Schrödinger bridge gives us a method of approximating score function. This is of independent interest. If I want to estimate score function, all I need is a lot of samples from that density row. And if I calculate the discrete Schrödinger bridge and take its conditional expectation, that would give me B, and then just B minus identity over epsilon, that would give me an approximation for the score function.
Medha, how much time do you have left?
I think I have 2 more slides,
Okay.
2 or 3.
Great.
Okay, so yes, so this is my explicit Euler update for the heat equation, identity minus epsilon over 2 gradient of log rho. And this is my Schrödinger bridge update, or the self-attention update over here. The intuition was set up in the previous slide, but concretely we prove in a theorem that they are indeed very close to each other. So one update step of the self-attention and the explicit Euler of the heat equation are very close to each other. In fact, they are small o epsilon close to each other. And then the final result is that indeed this approximation is universal, is uniform, in the sense that I can consider any time point. So not just the first step. I can consider all the steps between 0 to time capital T, and uniformly I will converge to the heat equation. And then quickly some simulations. So the histogram is showing the histogram is for the position of particles undergoing self-attention, doubly stochastic self-attention update, and then the solid lines are the analytically available density for heat equation when the starting distribution is this mixture of Gaussian. We consider Gaussian because that is one of the very few cases where we would explicitly know what the density is going to be at any time for heat equation, and then they very closely match to each other. So here are the snapshots for that animation. So this kind of confirms that if we look at the doubly stochastic self-attention in that particular configuration, the query transpose key is identity, and then the value is minus identity. In that particular configuration, if we run this doubly stochastic self-attention updates, they are the distribution of the particles is going to evolve as if it was undergoing the heat equation. In fact, they're equal. We prove that uniformly that thing converges to the heat equation. Thank you.
Any questions? Yes.
So if you go to the original definition of the attention algorithm, the exponent of softmax is given by this by one matrix times the other matrix transposed, and it is a bilinear form in X. And if you look at it, you can just take the symmetric part of WQ transpose WK, which defines a Gaussian probability distribution plus the anti-symmetric part. But if xi, xj, you know, and you just pair it, then the diagonal parts of that disappear. So basically, I would expect that if you don't choose WQ times WK's identity, that your heat equation would be defined with respect to a metric given by WQ transpose WK symmetric part inverse. Is that what shows up there? And basically, this is this is why the heat equation appears, because if you iterate that, then in every step you basically just average using a Gaussian.
Right. So what you're saying is that if this WQ transpose WK is, say, some matrix A.
Yeah, and A you can split it to A symmetric plus A antisymmetric. Then the asymmetric will dominate.
Yes.
Because it's X on both sides.
Right, right.
And this generates a heat flow.
I see. Interesting. Okay. That's okay. I'll share that with my group. It's an interesting observation. Yeah. Yes.
So related to what Thomas was just saying, is there analysis like this when you just use softmax rather than sync-form?
So we haven't done analysis on that, but the original paper that discussed doubly stochastic self-attention, they proved that it does not converge to a gradient flow like heat equation does, like this version, doubly stochastic version does. So I don't know how useful that is, but they say that if you were to take epsilon going to 0, there is an object that we recognize and understand well that like gradient flow that it converges to.
Could you please show the Sinkhorn algorithm?
It just alternates row and column normalization. You normalize the rows, then you normalize the columns, then you normalize the rows, then you normalize the columns.
Does it somehow get rid of the antisymmetric part?
Oh.
I'm not sure.
I don't know. It appears, I mean, this algorithm appears like in theoretical computer science, and it's pervasive. Like you can prove lots of things about it. It's surprisingly effective. Any other questions? Okay, thank you.